Welcome everyone again. Thank you for coming. So this is the second part of our ERIE Science Hour special on the EGU presentations that were related to ERIE that happened week before last. And so we've got two presentations today, one from Rohit and one from Stephy. And so Rohit, please take us away.
Thank you, Malcolm. So first, I'm going to talk what I gave presentation in EGU. It's not that long, and maybe the first part is kind of we know about it already because we are from EE project. So my main aim in this presentation was to give an introduction of the kind of simulations that we are going to perform in the Frontiers simulation in our work package. 1 second. Need to stop a little bit. So yeah, to start with, I will have this is the introduction of the European EDRICH Earth System Model project, and what we are trying to do and what's happening in our what will happen to our climate system when we will have eddy resolved, ocean eddy resolved in the ocean model. And then after that, we will have an understanding of what. Excuse me, can you still hear me?
Yeah, it goes in and out a little bit, but we can hear you.
Okay, I just can change because my headphone was telling that I have no power. Now maybe it's better. So yeah. So what this part, I think you know that we are trying to understand the climate system when we have the ocean eddies resolved. And then I tried to explain that in this project, we also have try to have a synergy with other kilometer scale projects like Destination Earth and NextGens. And what we try to do, one of the main goals is to do simulations, high-risk type simulations involving different models from Europe, where Max Planck Institute is also involved, and AVI is involved with IFS FISOM, and Max Planck Institute with ICON, BSc with IFS NEMO, and also from Met Office we have Hadron model, but we have this frontier simulations, high-risk simulations, where we have kind of 10 kilometer or 9 kilometer atmosphere resolution, 5 to 10 kilometer ocean resolution. We try to resolve mesoscale eddies or eddy-rich ocean and perform this kind of simulations where we first do a spin-up of 50 to 100 years, and then control simulations, which gets performed in parallel to the historical runs, and then we have different kind of scenario simulations. And in this presentation, I focused mainly on IFS FISOM control. This is kind of the coupled spin-up part of the simulations that we are going to do. And then in that simulations, we have used IFS FISOM with TCO 1279 IFS, which is kind of 9 kilometer atmosphere, and N5 FISOM, which is kind of 5 kilometer ocean, with this the model configuration. And in this presentation, I try to show the simulations, what happened from 1950 to 1980. It's a control with 1950 radiative forcing, symmetric radiative forcing, and the ocean. Before this simulation is performed, the ocean model, the FISOM, was initialized with EM4 for 5 years and ERA 5 boundary forcing. And after that, from 1950 onwards, it was coupled with IFS and allowed to run freely with the 1950 radiative forcing, the same states. So basically, first want to show you how the this is here we're showing 100-meter depth the ocean velocity, ocean currents, and you can see how the ocean eddies looks in the simulations. This is a period of 60 days in the year 32 of the simulation. And if you see the effect of these ocean eddies, you can see the sea surface temperature fields, which also has this meandering the eddy structures captured and you can see the tropical Pacific, this wave kind of pattern, and also in the subpolar regions, and also all the AD-rich regions are kind of well captured. And then now there is another animation from Nikolai to show you the subpolar North Atlantic. In this, will go through the entire year, and you can see here first the ocean current, ocean velocity, the U velocity, and U component ocean velocity at the top layer, and then you see the superimposed on the mixed layer depth structure, and you can see the meandering patterns and the mixed layer depth, and then it moves to the ocean surface temperature that's superimposed on this V velocity, and you can see how the ocean eddies are. And then now you can see some cyclones moving through this box area. So this means the run is happening, what we wanted to see, the eddy ocean eddies, and also the features that we are expected to see in high resolution. But in the climate-wise, are we doing something similar as we see in reality? To address that point, I show here the climatology of the IFS phase zone for the last 20 years of the simulations, and compare it with the ERA 5, an average from 1940 to 1960 in ERA 5. And you can see overall the 2-meter temperature climatology looks quite similar. It's the patterns and everything comes similar, and both are now here regraded into quarter-degree grid. So for comparison, and but if you look at the difference of these two climatologies as a whole, it looks quite same. But you can see there are regions like in the northern latitudes, which is much cooler than what we observed, what we expect from the ERA 5. But except that region, most of the other regions, they are very less biased. Mostly it's within the range of what we expect, except also the Eastern Tropical Equatorial Pacific. I think it's one of the another regions that we expect, we observed previously. Also colder bias, but the main area that stands out is this Nordic Seas and the Barents Sea region, going to the high latitudes, which has much colder 2-meter temperature. And our investigation finds that also this colder temperature happens from the drift that happened in the run. So after the run has started, here I'm showing you the global mean 2-meter temperature in the left-hand side, and the blue lines are the monthly means, and the orange line is showing you, orange curve is showing you the yearly means. And you see in the first 10 years there is a drift in the run, and after the 10, 15 years it's kind of minimized. There's not much drift in it. But this drift is mainly happening in the northern high latitudes. The temperature is getting colder because it goes hand in hand with an increase in the sea ice. So in that region, the sea ice is increasing. Because of that, it's making colder temperature, and that's mainly the reason of this drift. Which means that if we are able to resolve this issue, if it's an issue which could be possible, then maybe we might be having a stable state even earlier, because other regions are quite stable. Only this is the northern high latitude which is causing this drift. And then if we are able to understand what's causing this, maybe our spin up might not be, we will have a stable state quite early in this high resolution. So to confirm, I here show you the sea ice concentration. I have 1 or 2 figures which I didn't show in EGU, so this is one of them. So here the sea ice concentration in the first year, the run in the year 1, the sea ice concentration yearly mean, the mean sea ice concentration in the left-hand side. And you can see on the average, in the right-hand side, I show you the difference of the first last 10 years and the first 10 years. And you can see the region where we have seen this cold bias is the region where the sea ice is forming a lot. This is the sea ice area that I am showing in the percentage. So it's increasing this percentage in this right side. And if I look at the sea ice thickness, so it also shows the same. So here also the first year when the run has started, the yearly mean, and then this is the last 10 years minus the first 10 years average, and you can see all the marginal in the Arctic Ocean, how the sea ice thickness is increasing, and it's already quite high to start with, 5 to 6 meters in the depth region, but in the boundary region, in the Barents Sea and the regions where we have seen these high values, and we kind of, our first assumption, what our first hypothesis is that in this IFS model, it has a missing dynamical sea ice coupling. So the sea ice thickness is not coupled with the IFS model. IFS model assumes a constant thickness of 2 meters. And that kind of messes up the process and the coupling, and it tries to gives more flux to generate. So this is assuming 2 meter thickness, and kind of that messes up. So on the basis of that, we did some initial analysis with a very low resolution version, and we see that when there is a routine which allows a sea ice thickness coupling, and when we sea ice temperature on the skin, what is the temperature of the skin? If we put that temperature, this drift is much less. But we have to still try it out in a higher resolution, moderate resolution or higher resolution, to see what its impact is. But if we look at the overall climates in other factors, we figure that the model, although there is this issue in the northern high latitudes with the sea ice, we find quite a decent pattern of the precipitation. This is the annual mean precipitation in IFS free zone and the AR5, and you can see overall the patterns are captured quite well. Also over the land region, we have well captured the patterns. And then also this is the mean sea level pressure patterns and annual mean. And just to give you a mean idea of how the atmospheric parameters in the climatic sense is coming. So this is also the last 20-year average climatology. And here I show you a performance matrix of compared to the CMIP6. So it's a typical performance matrix. So to understand here, as green it gets, it's getting as better compared to the CMIP6 multimodal mean. And I'm showing you here the atmospheric parameters, so the cloud, total cloud cover, precipitation, U wind, and V wind at the 10 meter, and the 300 Pascal wind, the upper atmosphere, and also the 500 Pascal geopotential height. So overall, you can see a greening of this image compared to the multimodal mean. The total score is 0.6, which is kind of almost a 40% improvement compared to the CMIP6 models. And you can see precipitation, and in the X direction, you can see different regions. These averages are performed from starting in the left from the Arctic to going to the Antarctic. Basically, in the geopotential height, you can see in the tropical region, there is still some issues that we have the circulation features. But other than that, we have quite a decent improvement compared to the CMIP6. In that note, also, if you want to look at the ENSO and its variability, so you can see the ENSO variability where the 3.4 index during the last 20-year period, and it has El Niño, La Niña phases that you can see in the colored regions. And if I do a regression of that on the SST patterns, correlation of that with the SST patterns, you can see that it captures also the El Niño region, and its signature in the other ocean basins are also well captured. In that sense, I summarize here that the presented works shows the current effort in the European EGU System Model project that we are doing. I here show the couple simulations of the 30 years, starting from the ocean industrialized with the 1950 radiative portion. So what we see is shows the ocean eddy activity is quite good, and the global climate is also well simulated with marked improvement in the atmospheric parameters that you have seen. Although right now there is an issue in the Arctic sea ice. The Arctic sea ice is forming, and we assume that right now our initial hypothesis, which is getting supported, that the way it's coupled with the atmosphere need to be looked at to resolve this. And ENSO and its variability is also well captured. So in that note, I thank the EERIE for its funding for this work, and also thank you for your attention. This is one graph of the animation of the 10-meter wind speed, and you can see the cyclones forming in the North Atlantic and also in the Pacific Ocean. It's during the August and September months of one of the years, the year 32. So yeah, thanks. Yep. Anna-Marie, I see your.
Oh. Thank you very much. I mean, that's a very interesting.
I cannot hear you.
Oh.
Yeah, now I can hear you. Yeah,
okay.
That was my side.
So thank you very much. That was a very nice presentation. I would like to know whether this problem with coupling of the CIs was also present in the ECERS model, and if it was present in ECERS, why it was not detected before.
I'm not sure with the ECRs if it's also present there, and if it's happening there, maybe someone else who worked on that. But right now, I think what my understanding is, this issue was there, and then it was kind of fixed in the meanwhile, and now it's reappeared again when we run this model. So we know that this condition of the 2 meter thickness is there in the IFS, and we kind of fixed it before I arrived and did the simulations. That was understanding, but after doing the simulations, we are realizing that that issue is again coming up, and we need to resolve it. So that's. But with the ECR, I'm not sure if it's also, they also have some issue, I think, and, with that model. But if it's also related to that, it would be good to look at.
Well, thank you very much.
Okay, thanks, sir. I have a talk.
Could I jump in with a very quick question? First of all, thanks a lot for this nice presentation. Could you go to that slide where you show performance metrics plot? So with respect to CMIP and so on, with this green and purple colors there, yeah. What jumps out to me is that precipitation looks not so perfect. You were saying that when it gets greener, then it's better in general. But for example, if you have a look on Nino 3.4,
yes,
there it looks a little bit terrible, I would say, as it is super purple
it's
there.
in the tropical over the Nino region. It has some issues, but right now we are in the beginning phase. I don't know if it would get better when we have the real control. So it's. But in the tropical region, in the Nino region, we also have a bias in the SST. There is a little bit cold bias. Maybe that's the effect coming in the precipitation. If you remember the 2 meter temperature figure, it was having a little bit of cold bias in that region in the SSTs. And with our initial analysis, while we tried to figure out the CI issue, we also saw there is some kind of similarity over the equatorial Pacific also have an issue. So if we fix the CI issue, I don't know if it would also have an effect on this equatorial SST. But you're right, the tropical precipitation, especially on the Nino region, is not exactly doing better than the CMF6 multimodal.
Yeah, but that's also the most difficult metric that you could look at, basically. So thanks a lot for the clarification.
You're welcome. Thanks. Okay. If there is no more questions, maybe I would stop sharing. And Steffi can be present. I see that Malcolm has some issue with his laptop. So maybe Steffi can already start. Did I stop sharing? Yeah. Who is the other presenter? Yeah, Steffi. Oh, okay. Okay. Hi, Malcolm.
Hi, apologies. Apologies for that. My battery died. My laptop died.
Yeah, no problem. I just stopped sharing and asked Steffi to continue. But if you had any questions from my presentation, yeah, you can also while she's preparing. Yeah.
I don't know if anyone else. I guess one question: did you look at whether the AMOC changed during those first few decades to know whether it was so that the ice seems like the obvious thing, but whether the northward heat transport
I
changed?
will look at it because I need to perform some more analysis of the ocean in that area. So yeah, maybe in the next weeks I will have some figures on
Okay.
AMOC and the other
Right. Great.
Anne-Marie has a question that if it's an issue in the ECR model, I could not answer that because I didn't work with ECR model. If it's a similar issue remains in the ECR model, if you know something, then you can add from the high risk. But yeah.
Right. Okay. Oh.
Yeah.
Okay.
Thank you. Yeah. Sure.
Yeah, if you can hear me, Steffi, oddly, Michael's laptop also seemed to do that just now as well. I don't know why. I've never had that problem before. But it is a problem if we can't hear you. So Rohit, maybe I can ask, so has the sea ice thickness always been uncoupled? Is that some development still ongoing? I think you kind of touched on it a bit.
Yeah.
Some time ago, and then it was kind of fixed, this issue that I think the sea ice thickness is fixed, kind of. It works like if you have an AMIP simulations, maybe you need to, but for coupled, and this issue was realized before, and then now and we thought that it's kind of fixed, but now as we see it, that there might be that issue of this 2 meter thickness assumed by the IFS is kind of came back. So we trying to understand.
Okay.
There is a routine available which couples the temperature on the surface of the sea ice, which would resolve this issue. So in that sense, I can show maybe, yeah, for in that regard, there is this, it's with really, it's with really low resolution. So it's with TCO 79, but we have one of our colleagues performed the simulations just to check the effect of the sea ice temperature, the top of the temperature coupling. And so the blue lines, this one is showing without coupling. That was the case for my run, blue time series. And when you have the coupling, proper coupling, then you see the drift is kind of reduced, and it's kind of so blue and green are for the northern hemisphere, and the red and orange is in the southern hemisphere. So the southern hemisphere kind of is maybe the point that he was mentioning, that maybe it's more thermodynamic in the Arctic than in the Antarctic. It's more other processes which also plays a role how the sea ice would be. So we see.
Okay, so I think I
so
I understand better. So it's coupling of the ice thickness to IFS that's the issue.
Exactly. Yeah.
Okay, got you. Okay, right, I understand that better. Thank you. Yeah. Right.
So
hello, can you hear me?
Yes, now
Yes.
I can hear you.
Okay.
Yeah.
Well done.
Thank you. I tried 3 things, finally something worked. Yeah, maybe I should try sharing my screen.
Yep, please.
The test of whether anything will happen today.
Oh yes, great. So yeah, so Stephy's going to talk to us a little bit about mesoscale ocean sea ice coupling, I think.
Yeah. So I have the poster that I was presenting at EGU here, and I hope you can see this. And I think today my plan is to just walk you through my poster. So first of all, the whole topic is that we're working about the effects of eddies under sea ice. And in the first part of my project, I'm focusing on the southern hemisphere, so therefore the Antarctic sea ice. And so in my poster, I've put this 4 questions, mainly as to kind of initiate certain conversations for people that might come by my poster who are not familiar with Southern Ocean or who are not familiar with eddies and what are the challenges and what are we doing? What does ERIE as a project do to overcome those challenges, etc. So first the question is, why should we study the eddies in Southern Ocean, or overall, why does these polar oceans matter? And so for that, I cannot say too much, but overall, it has a key role in setting the meridional overturning circulation and also our climate. And the eddies also play a role in sort of setting the Antarctic circumpolar current structures and also in modulating certain exchanges, which we still have to investigate. And I just touch about the challenges that we face. And first thing is that because sea ice acts as a shield or a cover, most of our observation methods are quite limited in understanding the eddies under sea ice. So a lot of our satellites did not detect eddies under sea ice until recently. So there's a paper in 2023 that has started detecting eddies under sea ice, or they've developed methodology to produce certain algorithms that can do that. But yet, the amount of data that we have about eddies under sea ice is quite limited. And then also, a lot of our global models used to be coarse resolution to not be able to produce or simulate eddies in the high latitude. So that was another challenge. So with ERIE, with the eddy-rich simulation models, we are now able to have models that can actually resolve eddies in the high latitude and be able to investigate that. And then this is a bit about bit of an introduction, which is kind of a cheat sheet from my side, because a lot of people think of the ocean stratification to be sort of similar all over the place, but it's not true, especially in the sea ice zone of the polar regions, where you have cold water at the surface and warm water subsurface. So in the eddy sort of interaction, when you might expect like upwelling to bring cold water, that signs may flip. And so that's why I have this question here. So because there will be confusing results, and just to point back, okay, this is a different hemisphere and also a different region, polar region, that has different structure of the ocean stratification. And then I have pointers of 1, 2, 3, 4, so that people can go in order. The first one is to just show the general picture, so how the anticyclonic and cyclonic eddies behave in general. So you have the positive sea surface height in the anticyclone, negative sea surface height anomaly in the cyclonic, and then the rotation of the zonal and meridional velocity. So yeah, more or less they look like they're doing what they should be doing. And then I also show the sea surface temperature, the sea surface salinity, and this composite set is for all eddies under sea ice with the minimum concentration of 70%, which means I'm setting all the eddies that are under sea ice of 70% concentration of sea ice or more. And then this is also for the entire year. So I'm not looking at different annual seasonal changes. And the second part of this poster is now arguing that it is really important, especially in the polar regions, that we take into account the seasonality. So if you look at the center of the section, that is these polar stereographic plots. I hope you can see the cursor. Can someone confirm?
Yep, we can see it.
Okay, thank you. So in these polar stereographic plots, I'm showing the sea ice. So it's the climatology for that specific day, but 1 day of eddies. So there's both cyclones and anticyclones. And what I'm showing is different sea ice concentration contours to say that there's different sea ice concentrations and the regions where these exist, etc., are different. And we have to take into consideration the strong seasonality that exists in the polar regions. And if you composite certain characteristics of how the eddies behave as a whole, you might be losing certain strong seasonality in their behavior. And so for as sort of example variables, I'm taking temperature, salinity for the ocean, and then the thermodynamic sea ice growth as a sea ice variable. So here you can see in all of these panels, the summer, there is a strong summer, I would call it disturbance. And then in winter and spring, some of these signals start to become more clearer or stronger. And I have to make a bit of, what is it? How do you say it? Like, some of these results don't really make sense to us at the moment. Like, some of them are contradicting to the literature, and it needs to be investigated. At first, I was sort of scared that I made a bug in my code, but then we double checked, and the signal seems to be similar and consistent. So we still have to check why certain flip of signal has not happened. So if you have questions, I'm just saying that in advance that signal flip is present. So if I can zoom in, so we have the summer disturbance in each of them, and then as expected, when there is strong sea ice concentration in the anticyclonic, you do expect that the warmer water is upwell to the surface, and so you have a core warming. And I'm apologies, my color bar is not a great use here. And then in the cyclonic eddies, you retain the cold waters at the core. And then in the salinity, when you have warmer core, you would expect that the sea ice would melt and freshen the core. And then that is stronger in summer. And then in the winter and spring, the colder core would actually lead to a slightly increased growth of CIs and then brine rejection and salinity. So that you can expect. And then in the thermodynamic CIs growth one, you'd see that in both cases, overall, you see the positive signal, which, as I mentioned before, we have certain signals that seems to be consistent between anticyclonic and cyclonic, which needs to be investigated further. But obviously, you still have a strengthening or a strengthening of the signal at different seasons. So in these composites, again, we have a banding signal, which in the last 2 weeks when I was not working, my colleagues have actually made a huge progress in figuring that out and making headway in fixing that. So that's for them to explain. And then one other thing that I did is this is the seasonal sort of changes, but then there's also the annual evolution of that. And so the next thing I did is I only selected the core feature in each of these eddies and looked at different CIs concentration ranges. So the CIs that would belong to very weak CIs concentration, the eddies under the marginalized zone or weak CIs concentration, that is from 0 to 25%. And then the strongest would be the red one from 70 to 100%. And then look at how these relationships go. And also the anticyclonic is dashed and cyclonic is dotted. And when we look at that, there seems to be some stronger gradients when you go to weaker CI signals. So at this strongest or the highest CIS concentration, there seems to be less changes, whereas at the weaker CIS concentrations, the deviation seems to be stronger. That is kind of like the initial points that we identified, but a lot of things needs to be investigated further. And overall, the argument I have in my poster is that we need to understand what's happening in the polar regions with the eddies interacting with the ice and the ocean, how that modifies a lot of interactions. And as expected, there is potential for strong seasonality, and also under different CS concentrations, under different CS concentration ranges, those relationships can vary. And this is only the results from ICON model, but we need to do it with other models as well. So I think I'd leave the key points and discussions there, and I'm happy to take questions.
That's great. Thank you very much. That's very interesting. Yeah. Any questions, anyone? Maybe I'll ask an initial one. So you mentioned that there's limited amounts of observations. Is there enough to test any of the things that you've done already to check that the models are doing what the observations suggest, or are the observations too sketchy to be able to do that?
So if my memory is correct, I think there is 2012 to 19, so 7 years of daily eddy detection in the Southern Ocean. And I also at EGU met the team that is going to extend that until 2023. So there's going to be a longer data set. And I don't know when they will release that data set, but maybe before the end of EGU that might happen. Okay. So that could help us. And some of the things in their paper about how there's more cyclonic eddies, or the cyclonic eddies in the marginal ice zone seem to be responding more or having a seasonality, whereas anticyclones does not seem to have changes, etc. Are some curious questions that needs to be checked in. So I actually interacted with the person that is working on that observation, and they're very interested to see if those kind of relationships exist also in the model, which means we might be able to test that.
Okay, great. Other questions?
It's nearly 2 hours.
Yes, yes.
So,
Well,
Steffi,
oh, yeah, go on, Anne-Marie.
thank you very much. And I already asked a few questions in front of your poster, but I wonder whether we talked about that at EGU, the fact that the main effect in the Arctic that sea ice has on eddies is to damp them. So are you also investigating the strength of eddy and it's the seasonal cycle of the eddy strength?
I have not yet looked at how the strength of the eddies are changing, but yes, the frictional effect of the sea ice on the eddies is to dampen that. And I'm also talking to Vasco from AVI, who's also working on similar topics. And connected to the previous point that I made, that there's more there's more anticyclones than cyclones. There is a hypothesis that there are surface intensified cyclones that then split into anticyclones at subsurface and they drift off. So there is a chance that the frictional effect might also be leading to the differences in the density of the different types of eddies and so on. So, but that I'm not sure how much we can test it from EERIE, because if we only have 2D data in that level, I'm not sure if we can test that, but might be worth looking into. So I don't know, but definitely I agree that the dampening is there. I have not yet looked at the strength, but it's definitely something to be looked into. It's to me, it's more like it's just opened up a lot more questions to look into. So
Thank you very much.
thank you.
So maybe I can ask kind of final. So I understand that the SWAT satellite has been up for a while, and I think someone was telling me earlier this week that the data's not released yet, but they're gradually gathering data. Does that help? I don't know. Does SWAT give sea surface height data down to high latitudes, or I don't know.
I don't know how that would help, but also additionally, if my understanding is right, it's not just sea surface height at the high latitude. I don't know if they can overcome the presence of sea ice.
Yeah, okay, right.
I believe the paper in 2023 is doing certain additional steps so that they can, I don't know, I cannot remember it to cite it in that way, but they're doing certain additional steps to make an algorithm that can overcome the effect of the sea ice cover to still get the surface height. So maybe that will be applied on the data. That might help.
Yes, you could do on that. Yeah. Okay. Yeah. Great. Okay. Thank you. So thank you both to Steffi and to Rohit for those really interesting talks. Thank you all for staying around for a big chunk of your afternoon. I think it's been a really interesting hour and 3/4. Hopefully it's all been recorded and will appear on the website soon. And then before I forget, unfortunately, because my machine crashed, I've lost all of my nice markings, but if I remember rightly, the next science hour is on the 17th of June. It's now going to switch to Monday afternoons. And the next one is on the 17th of June, and I'm sure the details will be on the website soon if they're not already. So thank you all very much, and see you next time.